Welcome to Lesson 10D, 2D stagnation point flow, solution. In this lesson, we'll continue to discuss the Hyman's problem, which is 2D stagnation point flow. First, we'll non-dimensionalize the equation and then solve the similarity equation. We'll do this numerically. Here's the flow that we looked at last time, where we had an outer flow, psi equal bxy, and an inner boundary layer where we're trying to solve for u and v in the boundary layer. We had these assumptions and approximations. And in the previous lesson, we developed this similarity equation where capital F is a function of y. This is a third-order equation, and we have three boundary conditions, so we should be able to solve it. Before we solve it, let's non-dimensionalize the variables and equation. There's no inherent length scale in this problem, but we can create one from these two parameters, b and nu. We'll do this simply with dimensional reasoning. We know that kinematic viscosity has dimensions L squared over t, and this constant b has dimensions 1 over t. We know that because psi equal bxy in the outer flow. The dimensions of xy is L squared, and psi has dimensions of L squared over time. Therefore, b must be 1 over time. From these, we create a length scale, which is the square root of nu over b. Therefore, we'll define eta is y over square root of nu over b. What about capital F? F is a function of y, and you may recall that as y goes to infinity in the boundary layer, capital F approached y. Therefore, the dimensions of f are the same as that of y, which is length. So we'll let little f, which is a function of eta, be capital F, which is a function of y, over the length scale, square root of nu over b. Now both eta and f of eta are dimensionless. Let's plug these two definitions into our equation, which we had labeled equation 7. I'll write this out as f of y equals square root of nu over b times f of eta. And let's plug these into equation 7. Well, as we've seen before, this involves application of the chain rule. Since eta is y square root of b over nu, d eta dy is just square root of b over nu, and f of y is square root of nu over b f of eta. Therefore, capital F prime of y is square root of nu over b, that's just a constant, times f prime d eta dy. But d eta dy, when plugged in, gets rid of the square root of nu over b, so this simply becomes f prime, or f prime of eta. Similarly, f double prime of y is d dy of f prime of eta, which is f double prime of eta, d eta dy. And again, we apply this so that f double prime of y is square root of b over nu, f double prime of eta. Doing this one more time, we get another square root of b over nu. So f triple prime of y is b over nu, little f triple prime of eta. We'll plug all of these values for f and its derivatives into equation 7. The students can do this on their own. After a little bit of algebra, all the b's and nu's cancel out, and we end up with f triple prime plus f double prime plus 1 minus f prime squared equals 0. I'll call this equation 8. This is the final non-dimensional similarity equation for 2D stagnation point flow. What about the boundary conditions? Well, again, looking at our equations for f and f prime, the boundary conditions easily translate to f of 0 equals 0, f prime of 0 equals 0, and f prime of infinity equal 1. Thus we have three boundary conditions for a third order ODE, our equation 8. So it's mathematically well posed. But how do we solve it? The problem is that equation 8 is nonlinear. We have an f prime squared and an f double prime. So this is a third order nonlinear ODE. Well, no one's been able to solve this analytically. You're welcome to try, but it's relatively simple to solve on a computer.
I like this word, relatively.
Yes, Albert, everybody already knows that.
Yeah.
So let's solve this numerically using the Runge-Kutta technique, which we've already talked about in some previous lessons. But in our previous discussions, we applied Runge-Kutta to first-order ODEs. Here we have third order and nonlinear, but it turns out that we can break up the third order equation into three first order equations. This will be the key to solving these nonlinear higher order equations numerically. You can do this with any order equation. This one happens to be third order. Here's how we do it. We know that f triple prime is f double prime prime, and from our equation above, we put f triple prime on the left and everything else on the right. So we get f prime squared minus 1 minus f double prime. Next we write f prime prime equal f double prime, and f prime is just f prime. And now we have 3 variables and 3 derivatives, since I wrote these all in terms of derivatives. So in the Runge-Kutta solution, we let y1 equal f double prime, our first variable that has a derivative, y2 equal f prime, and y3 equal f. Thus we have the 3 dependent variables and their derivatives, which we can solve simultaneously in the Runge-Kutta technique. In my notation from previously, we use d as the derivative, so d1 is y1 prime, which from here, and using these definitions, becomes f prime squared minus 1 minus ff double prime, which is y2 squared minus 1 minus y3 y1. Similarly, d2 is y2 prime, which is f double prime, which from here is y1. Finally, the third derivative, defined as y3 prime, is f prime, which from here is y2. So these are the derivative equations that we will plug into the Runge-Kutta solution. We also write the boundary conditions in terms of the capital Y values. F of 0 equals 0 becomes y3 of 0 equals 0. F prime of 0 equals 0 becomes y2 of 0 equals 0. And f prime of infinity equal 1 becomes y2 of infinity equal 1. These are our boundary conditions in terms of dependent variables y1, y2, and y3 with these derivatives. So now we just plug this into our code, but not so fast. It turns out that for the Runge-Kutta technique to work, we march. So we must know or specify all the y values at the starting point, whether you're marching in time or in this case marching in eta. The starting point in our problem is eta equals 0 at the wall. In other words, we need to know y1 of 0, y2 of 0, and y3 of 0. Well, we have 2 of them. This one is 0 and this one is 0. But what about this guy? We don't know y1 of 0. Our third boundary condition is out at infinity. So what we'll do is guess y1 of 0 and march to infinity, which typically means eta going to 5 or 10 or some high number like that. And after we march, for at the edge of the boundary layer, we check our value of y2 at infinity. We want it to be 1, but unless you're really lucky with your initial guess, it will not be 1. Therefore, we must iterate, namely, we vary our guess for y1 of 0 until y2 of infinity goes to 1. When this happens, all 3 boundary conditions are satisfied, and then you're done with the problem. You can do this in any software of your choosing. I chose MATLAB here, and here's a printout of my code. This is my y1 at 0, the initial condition, which I guess until we achieve y2 equal 1 at the edge, or infinity. After some iteration, y1 at 0 is 1.23254 to several digits, and I went all the way out to 20, calling that infinity. Here's our Runge-Kutta subroutine in MATLAB that I showed before, and I'm solving all 3 equations simultaneously. Here are my 3 initial conditions for all 3 y's, and my function for the derivatives is given here. This represents the equation that I showed you, and these are the 2 simpler equations for these 2 derivatives. Here's a summary of the nondimensional similarity equation, the boundary conditions, the dependent variables, and their derivatives in terms of each other. And as I said, y2 squared minus 1 minus y3 y1 is what I typed in here. And recall that eta is y square root of b over nu, and f of y is square root of nu over b, f of eta. Here's a plot of my results, the similarity profiles from MATLAB. I plotted with the y variables on the horizontal axis and eta vertically, since eta goes from 0 at the wall to some high value. The blue profile is y2, which is f prime, which is proportional to u. This is our velocity profile, starting at the no-slip condition and asymptoting to a constant value of 1. If we had picked the wrong value of y1 at 0, this would asymptote to some value other than 1. The green line is y3, which we defined as f. This turns out to be proportional to negative v. And we know from the flow setup that near the stagnation point, v is negative and crosses into this boundary layer, and v is 0 at the wall, as it must be. Finally, the red curve is y1, or f double prime, which is proportional to the shear stress, since it's the derivative of f prime, or u. Thus we have our solution, not analytically, but numerically. Most importantly, the velocity profile for 2D stagnation point flow. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.